All right, this week we are looking at abnormal operating procedures, emergency operating procedures, and severe accident management guidelines, as well as our flexible coping strategies. So what does all that mean? Well, the all the stuff for your quiz this week is in your student text and the PowerPoint and the overview page and in this video. So you're going to have to get all the material to get everything. Let's start off talking about abnormal operating procedures. So we have several different tiers of procedures, and we have ABNs. That's our abnormal operating procedures. We have our EOPs, which are our emergency operating procedures. We have our SAGs, which are severe accident guidelines, and then we have our flexible coping strategies called FLEX. So ABNs, those are procedures. If you remember, we have things called anticipated operational occurrences, which are things that we expect to happen or have anticipated happening. We might have a relay fail that causes reactor water level to indicate differently than it does, than it is. And so we have procedures to address that. We've talked a little bit about ECCS systems, our emergency core cooling systems, and those are the systems that make sure that we meet the criteria for our beyond design bases event, where we keep the core cooled below 2200 degrees Fahrenheit in the worst case scenario, minimize the cladding oxidation, the generation of hydrogen, those 5 ECCS criteria. And when we're talking about ABNs, we're not talking about those types of scenarios yet. ABNs are, hey, we had this our high pressure core spray pump just started for some reason, so it thinks it got a start signal, and then it started up, and so we have an ABN that tells us what to do with that. So these are for our AOOs, anticipated operational occurrences, things that could plausibly happen and sometimes do. We deal with AOOs once in a while. Another thing is they restore the plant systems during off-normal conditions, not severe enough to require emergency operating procedures. So we're talking minor equipment failure. We have ABNs for severe weather. We have an ABN for high wind. Hey, if the wind is above 80 miles an hour, we enter ABN wind, and it tells us what to do. Hey, batten down some materials, send somebody to walk down, make sure there's nothing loose outside, no pallets or anything. It tells us to make an announcement saying, hey, don't be outside if you don't have to be. But we have ABNs for security events. So we have a lot of ABNs, and they're for things that try and put the plant in a safe condition before we escalate to EOPs. So let's talk about EOPs, emergency operating procedures. They mitigate the design basis accidents. So things that can happen to a reactor, an accident, but are within the design bases. An example, it might be if we have a leak, we have a pipe rupture or a valve blow apart in the dry well. And if you remember, we have our primary containment structure, and inside this primary containment there's our reactor, and inside the reactor is the core with the fuel. So the whole idea is, if you remember back to fission product barriers, we're trying to keep the fission products in the core. And so, but we have equipment that ties to the reactor vessel, and so we have steam pipes that come out. We have feed water pipes that go in. We have pumps inside the dry well. And we have, when I say primary containment, I mean, it's a little too low, isn't it? I mean the dry well and what we call the wet well. And down here is the wet well. This is a big pool of water. And we're going to talk about this as this suppression pool in a little bit. But we have pumps, we have all this equipment in the dry well in primary containment. And so let's say with all this equipment, we have valves. So let's say a valve blows apart and is starting to put a bunch of steam into primary containment, into the dry well. Well, then pressure starts going up. And as pressure starts going up, if it hits 1.68 pounds per square inch gauge, PSIG, then we have an entry condition into our EOPs. So our EOPs have entry conditions, for example, low reactor water level at plus 13 inches, drywall pressure, high drywall pressure, 1.68 pounds. Hey, we should have had a scram and it didn't scram, so we enter the EOPs. So there's entry conditions that put us in there. Now, what's different about ABNs and EOPs? ABNs are procedure based. They are, hey, I had this thing, fix this thing. Whereas EOPs aren't trying to necessarily fix a thing. They are what we call, in fact, let me put some more space on here. They're what we call symptom-based flow charts. Erase this here. And what I mean is if I have 1.68 pounds as an entry condition, I have plus 13 inches as an entry condition, failure to scram, I have all my entry conditions, and it says if any of these happen, then enter your EOP. And the EOP the first EOP has 3 legs on it. And each leg takes care of a part of the plant. So the first leg is level. The second leg is pressure. And the last leg is power. And this is on just our main or first EOP, dealing with just our primary parameters, I guess. And what it does is it says, hey, maintain level plus 13 to plus 54 inches, maintain pressure 800 to 1,000 pounds, and try and shut down the reactor. And then if you're unable to do the next step, the next block on that flow chart on each of these, it gives more actions. And it says, then do this, then do this, then do this. And it broadens the scope. For example, level band might go from plus 13 to plus 54 inches. It might go from down to minus 50 to plus 54 inches. And then if you can't do that, it might say minus 129 to 54 inches. And you try and then it gives you systems, and it tries to give you, hey, use this system, do this system, use this system. So these are symptom-based flow charts. It's not a book that you open up. These aren't procedural steps. These aren't, they're just symptom-based flow charts. And the other thing I wanted you to know about that is they're activated when plant parameters exceed protection system set points. So they have entry conditions. And they are required, and this is important, they are required by, in fact, I'm going to erase this entry conditions. And a more important piece for your quiz is they are required by regulatory, by a regulatory agency. They're required for our, gosh darn it, required by our regulatory agencies. That's important, okay? They say every nuclear power plant all across the country, every one of them is required to have our EOPs. There's a law that says we have to. So they're required by the NRC based on a new rig, and they mitigate design basis accidents using predefined step-by-step flow charts that are symptom-based. And then what happens if things get worse? What happens when we start to have fuel damage? What happens when if we start to have problems in the core that are not addressed by the EOPs? Well, then we're in the severe accident guidelines. Severe accident guidelines are the beyond BDB, beyond design bases. And the keyword tricky phrase, like there's something on your quiz about this is, when are they used? Well, they're used when core damage is happening, when fuel damage happens, or is imminent, or is about to happen. That's the key to getting into the SAGs. Once we start damaging the core, we're no longer in the EOPs. The EOPs assume core integrity, assume that we still have the fuel in place, safe, no fission product release, doing what it's supposed to be doing. So we have triggers that put us in the SAGs, the SAMGs, the Severe Accident Guidelines, initiated on specific degraded plant parameters. The key difference between the SAGs and the EOPs is the SAGs, oddly enough, are not required by the regulatory agencies. They are not required. So, what does that mean? Well, it means they're voluntary. The SAGs are voluntary. They say, hey, this is a good industry practice. Take a look at what happened at Fukushima. If you had SAGs, you would have had things in place to deal with something like that. Now, we don't ever expect to have to get into SAGs. So, the EOPs should keep the core safe, should keep the fuel intact, and we don't ever have expect to have core damage. But of course, it's happened at 3 Mile Island. So, sorry, I just lost my train of thought real quick. So it's voluntary. Oh, yeah, that's what I was saying. So it's voluntary. And that's the difference between these two, EOPs and SAGs. Completely voluntary. So what happens in a worst case scenario? We talk about Fukushima. Well, out of Fukushima, we started developing these flexible guideline strategies. Let me clear my page here. We started developing our flex guidelines. And this is our flexible coping strategies are based on symptom-driven safety function preservation. So what are safety function preservations? What does that even mean? Well, it means we need to have power. We need to have power for our pumps, our valves, our indications, and our logic. We have to have power to successfully operate the reactor. Okay, what else do we have to have? Well, we have to have water. We have to have water for cooling, inventory, cooling, and inventory. So what happened at Fukushima is they were going out to the parking lot and they were pulling 12-volt batteries out of cars, and they were bringing them into the control room and hooking them up behind the panels to try and get some indications. So we're going to talk about how did they know which indications. That's part of this week's topic as well. We'll get there, but let's finish talking about flex. And so if there was in Japan, when Fukushima happened, if there was a place in Japan, a big warehouse that had some extra pumps, some portable diesels, a bunch of fire hoses, a way to route water from, say, the ocean or a river, and some portable pumps and some portable diesel generators to get power to the plant. If they'd have been able to hook that stuff up within 24 to 48 hours, the damage would not have been as bad. So we in the United States, we looked at that and said, man, we should have some warehouses with some portable pumps, some diesel generators, and all the equipment we need to hook up our power and water at these nuclear power plants. So we have two centers called SAFER centers. And these centers, one is in Tennessee and one is in Arizona. And they're big warehouses that house all of this portable equipment, pumps, generators, all that. And they have all the connections needed to hook up to the power plants too. In fact, most of the nuclear power plants, I think all, had to go through and make modifications to some of their systems so that we had a common connections that matched the stuff that they were using for the SAFER center. So some group of people got together and they said, okay, we need to be able to hook up this portable pump to our Rixie system. What connection are we going to use? And the plant said, well, we have this, we have this, we have this. And they voted and they said, okay, we're going to go with this. And anybody that didn't have that had to modify their plant to make that connection fit. So now, whether you're getting equipment from Tennessee or Arizona, they roll in within 24 to 48 hours. They roll in these big trucks from these warehouses, and they start hooking up diesels. They start hooking up generators, or diesels are generators, the pumps. And so they give you power, they give you water, they start rolling out fire hoses and making connections. And they know they're going to fit because every power plant was modified so that they do fit. Now, these are required, these are implemented by an NRC order, and it's what they're call our Beyond Design Basis External Events, BDB. Nuclear power loves acronyms. So the response time is to deliver equipment within as early as 24 hours, but no later than 72 hours. And they're capable of plant-specific needs. They're meeting plant-specific needs. So the power plants out west, they'll get serviced by the Arizona one, and the plants out east will get serviced by the Tennessee one. This is important, there's a three-phase strategy, three-phase coping strategy. So the three parts of this strategy is, number one, our initial response. So the initial response uses installed safety systems. Okay, so that's phase one. Phase two of the flex strategy is transition. And in this transition phase, we start using the on-site portable equipment. So every station has some on-site portable equipment as well. And we want to start using that to prepare for so these first two steps are in that first 24 to 72 hours while we're waiting for the trucks to roll in. Step three is when the trucks roll in. And then we have support. We shift to the support from the safer centers, SAFER, the safer response centers. And once we shift to support from those, things are going to be pretty bleak at that point. That means we've lost all on-site power. We've lost the ability to pump water. Maybe we've lost inventory, or it can be pretty bleak. But when those trucks roll in and they hook up their hoses and they hook up their cables and they run their diesels and run their pumps, that should provide the necessary support for a beyond design basis external event. All right, so that's parts 1 and 2. We've got 4 things to cover tonight. Let's talk about part 3. When I said, how did the Fukushima operators know what instruments to hook this equipment up to? Well, it's because we have what we call PAM, post-accident monitoring. And this post-accident monitoring means we, before an event, we go through all our instrumentation and we say, hey, what will be essential to diagnose an issue during an accident? So essential instrumentation, essential instruments for diagnosis and response. So we went through and we identified, hey, we need this thing in the event of an accident. This parameter is something we're going to want to know. And we put a little dot next to the meter or the indication. whatever it is. And that tells us that it's necessary. That tells us it's a post accident monitoring item. So the Fukushima operators were just going through, say, okay, we need, oh, this one, this is a post accident monitor. It's got the little dot, and then they hook a battery up to it. So what kinds of things are we looking at for post accident monitoring? One of your quiz questions asks you give a couple examples. So here's some of the really strong key things that we want to worry about. We want to worry about the reactor pressure vessel, RPV, pressure. We want to worry about RPV level. So that tells us how much pressure is in the reactor. Do we have a bad leak? Is it depressurized? How much inventory level is how much inventory is in the reactor? How much water is in the reactor? Do we need to have we started uncovering fuel? So those are the two real big first ones. Other things we want to know is our suppression pool level. So when I talked about primary containment is made up of two things. It's made up of a dry well, and that dry well up here, this is the dry well, and then the wet well down here. And the wet well is a big pool of water, some 50,000 something gallons, I forget how much. And the idea of a suppression pool is if we have to, if we have our reactor, our primary containment, we have our reactor, and we need to depressurize it. Well, we have these safety relief valves that dump steam into the suppression pool. Now, if they didn't dump steam into the suppression pool, this steam would act like a leak and it would pressurize primary containment. It would pressurize the dry well, and that would be bad. So we put the outlet of this steam relief valve underwater, and we have this huge, massive pool of water, and that water absorbs that energy. And so it's not pressurizing containment, it's not releasing steam, it's not increasing temperature of the space. Eventually, the water will heat up a little bit, but it is such a massive amount of water that it can absorb all that energy from these safety relief valves coming out of the reactor. So another thing we want to monitor is because we want to know what primary containment pressure is. So primary containment pressure. And that's because that'll tell you if you have a leak. Like I said, if a pipe's broken, a valve blew apart, and it's leaking into primary containment, we want to know. Another way we can tell if we have a leak is primary containment radiation levels. So we monitor radiation levels. And then the last one, last real big one, is something that we talked about early on in the course when we were learning about logic systems and stuff. You learned about redundancy, and you learned about isolations and actuations, redundancy, all those things. So isolations are important. Isolations, if you remember, are, hey, we have something, an energy source that we want to isolate to prevent it from being released to another space or to the public. And so that's the isolations. And we want to see, did our main steam isolation valves closed? What other valves closed? What other things closed that stop radiation or steam or liquid from getting out of spaces that we don't, getting into spaces we don't want to get into? And ultimately, that all goes back to fission products. If we're experiencing fuel damage, all these things are carrying fission products with them, and it's being released to from one barrier to the next barrier to the next barrier, and eventually primary containment, secondary containment, and then to the people space. So we don't want that to happen. So our PAM instrumentation, this supports operator diagnosis. This is important. Operator diagnosis. They need to be able to say, hey, can we send people into this space? They need to be able to say, hey, the reactor has depressurized, which means it's a big leak, which means we need to figure out what level is, and we need to start adding water back into the reactor. We need to figure out where we need to isolate this if possible. So operator diagnosis, it verifies the operation of safety systems. Operation of safety systems. It detects breaches of fission product barriers. So it looks for release of fission products. And ultimately, I think it was 1 or 2 weeks ago, we talked about emergency classification levels and offsite response. And if you remember, those 4 emergency classification levels were, they start off at an unusual event, and then it goes up to an alert, and then a site area emergency, and then the last biggest one is a general emergency. And this PAM instrumentation is also used to help say, hey, this is what level of emergency we're in. This is our emergency classification. Because if you remember where we evacuate people on site, all unnecessary people on site are evacuated as site area emergency. We start evacuating people in the public in a general emergency. There's going to be protective action recommendations made at different levels here saying, hey, we've got these parks over here at Horn Rapids. We recommend to the local city, county, state, hey, we should remove people from here. Hey, we should evacuate the schools. Hey, we need people to start taking iodine. And we can't figure these things out. We can't figure which one we're in without that PAM, without that post-accident monitoring. So this last section is radiation monitoring systems. And so this is something we use all the time. We have radiation monitoring systems going all the time. Whether right now at the plant we're shut down, we're in an outage. If we're at 100% power, cruising along, we have different radiation monitors. So let's talk about some different types. We monitor our effluent. So effluent is things that are leaving different spaces. So this would be ventilation systems, for example. We monitor radiation levels in our ventilation systems. Spaces that might be is the reactor building, the rad waste, turbine building. All these different buildings, we monitor all the ventilation in for radiation levels. Another type of monitor, and then we have types of monitors like noble gas monitors. So noble gas monitors provide continuous indication of airborne gas release. And they are dual ranged normal operations, and then they go high range for accident operations. We also have particulate and iodine monitors. And those particulate and iodine monitors are more like weekly samples that we do, that we analyze. And they use filters and traps. And then we monitor them weekly. And so this is what's going on all the time. But we have, during accidents, we want to check and see if we have fission products released into containment. And so we have LOCA, loss of coolant accident, rad monitors. We also have area radiation monitors. We have airborne rad monitors, and we have dosimetry. So let's talk about each of these. The LOCRAD monitors are looking for a significant rise in radiation. So right up against containment at power, we might see as the most 1 rem per hour background levels in the really hottest spots, right up on the containment. But if we have an accident, that could go up to like 70 rem per hour. So we want to detect those fission products in containment. And that's with a cladding failure. If we lose cladding, if we lose that, then those will go off. If cladding releases fission products, then those will go off, and we say, hey, we got a leak, we got fission product release. Area rad monitors, they detect gamma throughout the plant. They're used for access and diagnostics. Don't know why I scribbled that out instead of just erasing. Area rad monitors monitor gamma radiation levels, and if we say, hey, we need to send somebody in to isolate this thing, okay, what's the radiation levels? Well, they look at the area rad monitors and they say, okay, radiation levels are here, this amount, and then they use that to diagnose, is it safe to send them in or not? And so that's our radiation monitors. We have airborne rad monitors. Airborne is real time. They have real time alarms for airborne hazards. And then we have dosimetry. So we have a couple different types of dosimetry. We have what we call a DLR, a dose of legal record, dosimetry of legal record. And it's an off-site analyzed. And what that means is I keep one on my badge. Every nuclear worker has one. And you wear it when you're at work. You just stays with you. I don't have to have it like on me here right now at home. It stays on my badge. It's next to the front door on my badge. And when I put my badge on, I'm then wearing my dosimetry and I go to work. And then every quarter, every 3 months, we exchange it, and then they send all those in and they get read. And so that's the DLR. Oops. Now, if I am looking to go into the plant, into the reactor plant, and go into the radiation area, then I'll put on a second dosimeter called an ED, electronic dosimeter. And it tracks live dose rate and accumulated dose. So I don't have an example one here, but you clip it on your badge. You have to wear it on your about chest level in front of you. But it has a little LCD readout. And on that LCD readout, you push a button, it'll say, this is your dose rate. Or you press a button again, and it'll tell you how this is your dose. So it's a continuously live count. And you turn it in at the end of the day before you go home. So you pick it up at work inside the radiation area, and then you put it back when you leave. And it tracks your dose for whatever you're doing there. We also have a pocket ion chamber. Those are issued in emergencies. It's a tube, and we'll just hand those out in a real emergency, and that gives you total dose. And so you can see your total dose as you're going through the emergency. It wouldn't be something that's checked out and collected at the end of the day. This is, hey, this is your dose during this accident. So that's the dosimetry. And that is all the things we wanted to cover this week. Let me double check. accident management procedures, flexible coping strategies, critical parameter monitoring post-accident instrumentation, and radiation monitoring systems. Yeah. All right. I hope you enjoyed this. I hope you got something out of it. Leave a comment if you have any questions. Thanks.